This is Module 7, Lecture Notes 13. In the book before class, you read a lot about how atoms came to be as we know them today. You read about how different scientists tried to figure out what was inside of an atom without actually being able to see inside of it. They did experiments, scientists like J.J. Thomson, Rutherford, Dalton. They conducted different experiments that you read about in order to figure out what types of particles were actually inside atoms. One thing that most of them agreed on was that there are some sort of charges inside atoms. Atoms contain positive charges and negative charges, and overall, most of matter on Earth is neutral, which means it doesn't have a charge. If you've ever played with magnets before, you know that charges that are alike tend to repel each other. They push away. But opposite charges, if you were to flip the magnet over, they often attract. Okay? It says every substance on Earth has electrical charges, and that's because there are positive and negative charges in atoms, and every substance on Earth is made up of atoms. However, most of matter is neutral because the positive and negative charges are balanced. So let's look at what the current model of the atom would look like today. So using the experiments that these scientists in the past have done, we have arrived at this model of the atom. It has a bunch of fuzzy stuff on the outside, which we call the electron cloud. And this is where electrons are moving around the nucleus. The center of the atom we call the nucleus. And inside the nucleus, we have protons and neutrons. Okay, and over here to the side, I've told you that electrons are the negatively charged particles. Protons, if you think of the prefix pro, they are positively charged. And neutrons are neutral. And we often use a lowercase n to talk about them. Okay, so what makes atoms different from each other? What makes an atom of oxygen different from an atom of nitrogen or different from an atom of bromine? Well, the answer to that is that each element contains different numbers of electrons, protons, and neutrons, depending on what type of atom it is. Okay, so let's look at how we can figure out from the periodic table how many of each type of those subatomic particles we have. So these three particles, you may often hear them called subatomic particles. They are particles that are inside of the atom, smaller than the atom as a whole. If you don't have your periodic table, go ahead and grab it. We're going to look at the element oxygen for our example. At the top of each periodic table square, your large number is called your atomic number. And this tells you how many protons are in the atom. We know in a neutral atom that the number of positive charges must equal the number of negative charges. So if you know the number of protons, you know the number of electrons as well in a neutral atom. This little number at the bottom is called the mass number. And it is found by taking the number of protons plus the number of neutrons. So the mass is protons and neutrons put together. Okay, so if you have a periodic table, you will be getting your information for the atomic number and the mass number from the periodic table square itself. But if you're not looking at a periodic table, I want to show you two ways you might see your element written. One way is you might see the symbol in the middle. You'll see the mass in the upper left-hand corner, and you'll see the atomic number in the bottom left-hand corner. So this is the same way of writing this element here. And you can even make a little note that this is the mass and this is the atomic number. Okay. And lastly, you may see the whole name of the element written out, hyphen the mass. So those are just some shorthand ways that you can see the same thing written. We're going to jump into a couple examples where I'm going to ask you to find the number of protons, neutrons, and electrons in different elements. Let's start by doing one together. Let's finish our oxygen example. I want you to work with oxygen 16. Okay, so you would go to your periodic table and you would see that oxygen is element number 8. Its mass, I've already told you, is 16. The number of protons will always be equal to the atomic number. So if I have the atomic number of 8, I know I have 8 protons, and I also have 8 electrons because it's neutral. And then to figure out your neutrons, you just need to subtract. Mass minus protons equals neutrons. I would like you to try these two examples by yourself. Copper 65 and silicon 29. Use these as your mass and figure out the rest. Okay, go ahead and check your answers. For copper, the atomic number is 29, so I can fill in the protons and the electrons. Because I gave you the mass, I want you to use the mass I gave you and subtract the atomic number from it to get 36 neutrons. Same thing for our silicon row. Now some of you may be asking, why can we not use the atomic mass of copper that's found on the periodic table? That is a wonderful question. If I hadn't given it to you, you could use this mass, and you would need to because you wouldn't have had enough information. Often these masses on the periodic table are not whole numbers, so you could have rounded to the whole number 64 and used it in your problem. However, that would have changed your number of neutrons. And I'll talk about that here in this bottom section, what that means. But on your homework and on quizzes and tests in your chemistry class, the mass will often be given to you so that we all come up with the exact same answer for the number of neutrons. Okay, let's jump down here to this bottom section, and I think for some of you it will answer the question about why there are not whole numbers for our masses on the periodic table. And the reason for that are something called isotopes. Here's your definition. Isotopes of an element have the same numbers of protons and electrons, but different numbers of neutrons. All right, so let's look at these two pictures that I have for you. Both of these nucleuses have 11 protons in them. So what element is this a picture of? 11 protons. This is the element sodium because it's element number 11. These are both sodium atoms. Okay, let's dig a little deeper. This one has 11 electrons, so does this one. So they have the same number of protons and electrons, but they have different numbers of neutrons. This one on the left has 12 neutrons, and this one on the right has 13 neutrons. These are isotopes of sodium. They're the same element, but they have different numbers of neutrons in the nucleus. So that also means they have different masses. This one is slightly heavier because it has more neutrons. So if we were to write the notation for this sodium atom, this one would be sodium 23, and this one would be sodium 24. Remember, you add the protons and the neutrons to get the mass. Both of these will have the same chemical properties because they're the same element. They're just isotopes of each other with slightly different masses. So what does that mean for our periodic table? Okay, the numbers for the masses on your periodic table are a weighted average of all of the isotopes that exist for a certain element. Take a look at this pretty cool table in one of my chemistry textbooks. It goes through some of the most common elements and it shows you the most common isotopes that exist. So if we look at hydrogen, there's hydrogen with a mass of 1, and that's 99% of all the hydrogen on Earth. There's hydrogen 2, and there's hydrogen 3. So if we were to take the weighted average of those masses, that's how we arrive at the atomic mass of hydrogen being a little bit greater than 1. You can see there's carbon-12. There's also an isotope of carbon called carbon-13. So when we take the weighted average of those two isotopes, we arrive at the atomic mass of 12.011. And that's why the atomic masses are not perfect whole numbers, because of isotopes. On the back of your paper, you will see 2 example problems, and these are the type of problems you may get in your homework or on a quiz or a test to show that you understand how to find these particles in an atom. So it says how many protons, neutrons, and electrons are in an iodine 129 atom. Okay, I'd like you to try that one and then write the name and symbol for an atom that has 10 protons, 10 electrons, and 11 neutrons. Take a second to do those and we will come back and check our answer. Okay, so I went to my periodic table and I looked at iodine and saw that it's element number 53. So I know it has 53 protons, 53 electrons. To find the neutrons, you will always take the mass that's given to you in the problem, subtract your protons, and get your neutrons, 76. For the last one, we know that an element with 10 protons is the element neon. So it wants us to write the name and the symbol. So we could do this like this. Neon dash the mass, 21 protons plus neutrons. Or we could also write it Ne with the mass and the atomic number, like that. All right, so that wraps up the section on atomic particles and how to find the number of each of them in a specific atom of an element. Okay, also in this same section, we're going to start to look at waves and how they behave. Okay, we're going to talk about waves of light because as scientists were studying how atoms, how they thought atoms looked back then, they also got into the study of the nature of light. And many scientists thought that light behaves as a wave. Okay, light is actually not matter. It does not have a mass and it does not take up space. Okay, here I've written that light sometimes behaves as a particle and sometimes behaves as a wave. Since we're less familiar with waves, let's define some of the important characteristics of a wave. So picture this like a slinky. Okay, you're shaking it up and down, up and down, up and down at a steady pace. The distance between 2 crests, or you could even do 2 troughs, that is called the wavelength. And I remember length like the length of something. How long is this wave? And the symbol for wavelength is the Greek letter lambda. It's the distance between crests or troughs of a wave. If you draw a center reference line on your wave, you can look at the amplitude, and that is A, and that is the measure of the height of the crests or the troughs of the wave. So that is the height. Okay, and then frequency is defined as the number of waves that pass in a given second. Okay, so think about you're shaking your slinky up and down, up and down, up and down. How many waves pass a point in each second? That is the frequency of your wave. And the units for frequency are going to be hertz or 1/seconds. Okay, below here you will see something called an electromagnetic spectrum. And it takes lots of different types of waves that we encounter in our everyday lives, and it puts them on some sort of a scale. Okay, let's look at what some of these are. Radio waves, TV waves, microwaves, infrared radiation. This skinny sliver here, I want you to label visible light. This is the portion of the electromagnetic spectrum that we can see with the naked eye. Ultraviolet radiation, X-rays, gamma rays, and cosmic rays. Okay, so lined up on a scale, we can compare what those waves would look like in reference to each other. Okay, so I've drawn a wave up here to show you that when we're on this left part of the scale, our waves move very slowly, and as we get over here, we speed up, speed up, speed up, speed up, speed up. We're going really fast when we get to the right side. So what can we say about the frequency over here on the left? Is it high or is it low? Go back to your definition of frequency, the number of waves that pass in a given second. Well, over here at this part of the spectrum, we have a low frequency. Radio waves going up and down. And as we move to the right, we have a high frequency. What does that do to the wavelength, the distance between the crests? Well, over here, if we were to measure the distance between these two crests, look how spread apart they are. Here, we have a long wavelength, or a high wavelength. It's long. And as we move over to the cosmic rays, they're going so fast that they have a very short wavelength. Okay, so one thing that is very important to get out of this section is that frequency and wavelength have an inverse relationship. When one is high, the other is low. If you have a low frequency, you have a long wavelength, and vice versa. The other thing that I want to make sure to point out in this section on light is that within visible light, within this skinny portion that we can see with our eyes, the wavelength of light corresponds to a certain color. Okay, so if you think about a rainbow, red, orange, yellow, green, blue, purple, each of those individual colors corresponds to a different wavelength of light. So I've kind of blown up this visible spectrum here to show you that over on this end, red light has a much lower frequency than purple light. Okay, think red, slow, and we're speeding up, speeding up, speeding up, speeding up, just like this wave up here. That is very important to know for this section. All right, so we learned that frequency and wavelength have an inverse relationship. When one is high, the other is low. So what can we do with that? We can say that the speed of light, represented by the constant c, is equal to the frequency times the wavelength. When one is high, the other is low. So we're going to do some calculations with this relationship. C is always 3 times 10 to the 8th meters per second. It's a constant, and it's called your speed of light constant. It will always be the same in each problem. You will just be plugging in your speed of light and a value that you know to solve for the other one. Okay, I also have a triangle to show you. You might have seen this before. I think we might have looked at it in the density section, but it helps you figure out what variable you need to solve for. The speed of light equals frequency times wavelength. So all you're going to do is you're going to take your finger and you're going to put it over what you are asked to find. If I want wavelength, here's my equation. If I'm asked to find frequency, here's my equation. And that should help you with the algebra in these problems. So let's look at our first example. A violet light has a wavelength of 435 nanometers. Hold up right there. Nanometers, look at that unit. I'm going to be pairing that with the speed of light constant, which is in meters. You want to make sure that your units agree before you plug them in. Whenever you get something in nanometers, you're going to need to switch that to meters. The way that you're going to convert that is nanometers is the same as 10 to the negative 9th. Okay, so we can go ahead and write this number as 4.35 times 10 to the negative 7th. And you can do these in your calculator if you want, and this is what you should get. But just know that nanometers, you're going to take your number and you're going to do it, put your decimal here and do it to the negative 7th. And this will switch the nanometers into meters. Okay, once you've made sure that your units for your speed of light agree with the numbers given in your problem, you're ready to solve for what they're asking you to find. And in this problem, it says, what is the frequency? So I'm going to cover up frequency, and I see that my equation is speed of light divided by wavelength. 3 times 10 to the 8th meters per second divided by 4.35 times 10 to the negative 7th. When you are doing these problems, you must use the E button for these to come out correctly. So this is what it would look like. 3E8 divided by 4.35 E negative, not the minus button, negative 7. And I get 6.9 times 10 to the 14th. If you're not getting that on your calculator, please make sure that you're plugging it in the proper way. And what units do I put on frequency? If you're going to cancel units, your meters cancel, and I have per second or 1/seconds. That is the same thing as hertz. 6.9 times 10 to the 14th hertz. All right, I'd like you to try to set up the second one, get as far as you can, and then come back here and we will check it together. In this problem, I'm asked to find wavelength. So if I cover up wavelength, I have speed of light divided by frequency. I've set that up here, and I'm ready to put it in my calculator. 3E8 divided by 4.98 E14th. And I get this number. If you want to put that in scientific notation, on these calculators, you can press second SCI and go over, and it will put it in scientific notation for you, or you can just count the decimal places. 6.02 times 10 to the negative 7th. What unit would I put on that? Well, remember that per second and hertz are the same thing. So those would cancel, and I'm left with meters. Whew, good, that makes sense. Wavelength is a length, and it should be in meters. That answers the first part of this question. What is the wavelength? Sometimes you will be asked a follow-up question. Can you figure out what color this wavelength corresponds to? So they want to know what color of light would this wavelength correspond to? All of these are in nanometers. So remember, meters can be converted to nanometers pretty easily. Remember our conversion here. So this is the same thing as 602 nanometers. What color are we talking about? We are talking about yellow light. Okay, so that's just a little follow-up question to apply your answer to the electromagnetic spectrum. Okay, this information at the bottom of your note sheet is more for the lab that you will be doing in class with your teachers. And they will explain this, but if you want to go ahead and read it, then you will have some sort of a background. But what you guys are going to be doing in the lab is you're going to be exciting electrons. So picture an electron, and it's in its ground state. Okay? If you give that electron some energy, and you can do that by friction, you can do that by heating it up. There are several ways that you can give an electron energy, but if you give it energy, it's going to jump up to a higher energy level. And it won't stay there forever, but on its way back down to the ground state, it gives off light that you can see. Okay? And you're going to be doing that, and you will actually be able to see some of the light given off, and it will be on the electromagnetic spectrum. It will probably appear blue or purple, or it will fall here in the ultraviolet region of your spectrum. I really like this experiment. I think it's pretty cool, so I hope you guys have a lot of fun with it in class.